In this video, we're going to try to combine all of the skills that we've acquired up to this point, and we're going to try to use them to actually predict the structure of a molecule just by looking at the spectrum for that molecule and by being given a little bit of a hint by the molecular formula. But before we do that, we actually have to learn one more skill, which is we have to talk about this topic of what's called degree of unsaturation. So this feature, this degree of unsaturation, it actually gives us information about the summation of the number of pi bonds within the molecule and the number of rings within the molecule. Now, the pi bond is a very rigorous way of just saying we're trying to sum the total number of double bonds in a molecule. So if we have a molecule with this double bond, one of these bonds that make up the double bond is composed of a pi bond, and the other bond is being made up of a sigma bond. A little bit of a review from Organic Chem 1. One other thing that we can say is if we go from a double bond to a triple bond, we actually have 2 pi bonds in this molecule. So this molecule would have 2 pi's. So let's go ahead and talk about the actual calculation we can do for the degree of unsaturation. It's actually a relatively simple calculation. The way that I do the degree of unsaturation is I start off with the number of carbons in the molecule, so I'll say number of carbons, and then I'm going to take the number of hydrogens. We're going to divide that by 2. We're going to subtract the number of halogens, so I'm just going to say any kind of halogen, so fluorine, chlorine, bromine. I'm just going to abbreviate by saying X. And so we're going to divide that number by 2. If we have any nitrogens, we're going to count the number of nitrogens, and we're actually going to divide that by 2, but in this case we have to add these to our total. And then at the very end, no matter what, we have to add 1 to the total. So number of carbons minus hydrogens divided by 2 minus X divided by 2, where X is a halogen, and minus nitrogen divided by 2, and then we have to add 1. So for this molecule, the way we would do the calculations is we'd say, well, we've got 4 carbons, we've got 8 hydrogens divided by 2, we have 2 halogens divided by 2, we don't have any nitrogens, so we're just going to ignore this term, and then we're going to tack on 1 at the very, very end. So what we've got is 4 minus 1 plus 1. So overall it looks like this 4 minus 4, these guys cancel out, and then minus 1 plus 1, these guys cancel out. So it looks like our degree of unsaturation is 0 for this molecule. So although a DU of 1 seems somewhat anticlimactic, it actually gives us a pretty good amount of usable info. So if you are lucky enough to have a degree of unsaturation of 0, you can actually say a couple things. The first thing you can say is that you have no double bonds in the molecule. You can say you have no double bonds in the molecule, and by that same token you could say no triple bonds, and you could say that you have no rings. So you have no pi bonds or no double bonds, and you have no rings, or another way of saying it is that the molecule is going to be linear. So if the molecule is linear, you don't have to worry about crazy structures like benzene rings or like cyclopropane or cyclohexane or anything like that. So right off the bat, this is actually some pretty good info to kind of take forward. And this is the first thing I would always suggest to do right at the very beginning before you do anything else. If you're given the molecular formula, go ahead, calculate the degree of unsaturation, and figure out what kind of generalized features you can have for your molecule. After that, I actually have kind of a 4 to 5 part process that I try to follow whenever I'm trying to solve these types of problems. So I'm going to introduce you to my problem solving method, and if you like it, wonderful. You don't have to use this problem solving method, but I find it very helpful. The first thing that I do whenever I've been given a spectrum and my molecular formula, obviously after the degree of unsaturation calculation, is what I'll do is I'll take my peaks and I'll write down everything that I have in a data table. And my data table looks very similar to some of the other practice problems we've done. I'll throw in the ppm, the integration, and the split. I'll put the integration in parentheses just so I don't confuse it with the ppm, and I'll also kind of list my peaks as kind of an A, B, C notation. So first things first here, obviously we can figure out the ppm and the splitting pretty quickly. However, in this case, I haven't been given any kind of integration numbers, so let's go ahead and figure that out just kind of by qualitative analysis using my little digital ruler. So I took a look at my smallest peak, and I'm going to kind of compare that to the biggest peak. So I've got one little small peak here, there, and then I got a third peak right there. So overall it looks like for every one of the small peaks I've got 1, 2, 3 small peaks for the big peak. So it looks like the relative integration at least is going to be something like 1 to, that looks like 3. And then at this point, what I'd always suggest doing is, well, these are relative, so you always want to be a little bit skeptical. So make sure that you always double check to see if you actually have gotten to the actual number of hydrogens, which we see in this case is 8 hydrogens. So 3 plus 4 isn't quite there, so we're just going to figure out our correction factor. So we have a total of 4 in the molecule from what we can see. We've got some correction factor, and then we have a total of 8. So it looks like our correction factor is going to be 2. So we're going to have a correction factor of 2. So after I multiply everything out, I'm going to get 2 over here for my actual number, and looks like I'm going to have multiply by 2 is going to get 6 over here for my actual number of hydrogens. So let's go ahead and get rid of all this other junk just to keep things nice and neat. And so now I can be very confident that this peak is 2 hydrogens and this peak is 6 hydrogens. So now it's time to actually list our peaks out in the data table. Now, what I'd recommend here is always try to be consistent in the way that you travel. I usually travel upfield to downfield, and I just kind of start labeling my peaks. So I'll label this peak A, and because I have colors, I'll use colors to make this a little bit more accessible, and I'll call this guy peak B. So if I start off with peak A, this is going to be peak A. The ppm for that's like 1.2-ish. And the integration we now know is 6, and these look like very simple singlets. So this is going to be a singlet right over here, and this peak B over here is going to be around 3.3-ish, somewhere in there, so 3.3. We know this has 2 hydrogens, and we have also a split of a singlet. Okay, so this brings us to the second part of the 4 to 5 part method, and that's going to be, we're going to have to do some work with trying to figure out what kind of hydrogen sets we might have. And it's going to be really useful at this point in the game to start thinking about these hydrogen sets as puzzle pieces. So just like you get a puzzle, you have like a 1,000-piece puzzle, you have all these puzzle pieces that you have to try to fit together. This is the exact same thing that we're going to have to do here. We're going to have to take puzzle pieces of, CH, CH2, CH3 groups, and whatever other, oxygen, nitrogen, carbon. We're going to have to take these puzzle pieces and we're going to have to put them together. However, unlike a puzzle that you can buy from the store where you are conveniently given the puzzle pieces, nobody's giving you the puzzle pieces here. So part of the challenge is to actually come up with your own puzzle pieces that you'll then have to put together. So second part of the challenge is coming up with puzzle pieces. So let's start with the easy peak. So this peak B has 2 hydrogens associated with it. And what we're going to do is say that if we have these 2 hydrogens, they have to be equivalent. More than likely, these 2 hydrogens are going to be attached to a carbon. So the easy way to explain this is with a CH2 group. So here are my CH2 hydrogens, and I'm going to just say that these are hydrogen set B. And so one thing I've done is I've just attached them to a carbon because that just seems like a safe choice. It's pretty likely. Other than that, I've put them on an sp3 carbon. And the reason for that is, again, the degree of unsaturation said that we didn't have any double bonds, so everything has to be sp3. Because of that, though, that means that this carbon has to have at least 2 other groups attached to them, but we don't know what they are yet. So the way that I deal with this is, just so I don't confuse myself later on, I just acknowledge that I have no idea what these groups are, so I just draw little squiggly lines right here and right here, and I just say, hey, this carbon is attached to 2 other things, but I have no idea what they are quite yet. Okay, so then let's walk up to peak A. Now peak A has an integration of 6, and there are actually a couple ways that we could try to interpret that integration. We definitely can't take a carbon and just willy-nilly attach 1, 2, 3, 4, 5, 6 hydrogens to that carbon, because that's definitely violating the octet rule for this carbon. So if you remember from OChem 1, we can't actually put any more than 4 groups on the carbon, so this guy's right out. So then that leaves us with 2 main likely possibilities. The first possibility is that we can distribute these 6 hydrogens between 3 CH2 groups. So this is definitely one possibility, 2, 4, 6 hydrogens, that would make sense. Or we could also take this, and instead of having 3 CH2 groups, we could have 2 CH3 groups. Okay, so it actually looks like we're in a little bit of a pickle, but I do have some generalized guidance for how to get through this. So if you are faced with this kind of impasse where you're not sure which puzzle piece possibility to go with, the way that I would recommend starting off is to just go with the possibility that has you making the fewest number of assumptions. And the way you can think about this is that if you are going to guess that you have 3 puzzle pieces, you're making 3 assumptions. Versus if you say, well, maybe I have 2 puzzle pieces, you're only making 2 assumptions in this case. Experience has told me that it's always better to start off with making the least number of assumptions, and a lot of the times you don't have to backtrack after that. Now, sometimes you do, but the majority of times you don't. So the way I'm going to go forward is just make the assumption that we have two CH3 groups, and these are going to both be hydrogen set A. Okay, so after we take care of the puzzle pieces that are associated with the hydrogen, we definitely need to take a moment, go on to another step, which is we want to see if we can count for any other pieces that we haven't talked about quite yet. So if you look at the number of hydrogens, we've got 1, 2, 3, 6, 7, 8. So we've actually checked off all 8 of these hydrogens, no problem. And so now let's try to count our carbons, and then we'll count our bromines. So we've got 1 carbon here, 1 carbon here, 1 carbon here for a total of 3 carbons. But if you look up here at the molecular formula, we've got a total of 4, which means that there's 1 carbon that's unaccounted for. So what we could say is that, well, we could take that carbon, and we know that carbon is not attached to a hydrogen, or else it would have been in this set right here. So we could either have a carbon that's maybe a carbonyl, we could have a carbon that's got, 4 things attached to it that isn't a hydrogen, and we could potentially have, carbons on double bonds, something like that. However, if you look back at the DU, or the degree of unsaturation, this is a number that keeps on giving and giving. So we found out at the very beginning that the molecule doesn't have any double bonds. So we can X-nay on the ketone K, and we can actually also get rid of the alkene, so pig Latin. So we're going to get rid of the ketone, and we're going to get rid of the alkene, which means that we've got some other carbon that has 4 things attached, and it's not a hydrogen. Other than that, so now that we've gotten rid of our carbons, we've gotten rid of those, we've got 2 other bromines that we have to deal with. So since bromine can only be bound to, one other thing, we'll have 2 different bromines like this. And so now we've actually done a pretty good job of guessing at what our puzzle pieces are going to be. Okay, so the 4th step is actually, now that we've made our puzzle pieces, we get to put them together. So one thing before we get going is to really think about these splitting patterns. So these splitting patterns are, say that both of these guys are singlets, which mean that they shouldn't have any neighboring hydrogens that are vicinal. So one possibility that we're going to try to discount right from the get-go, something that's very tempting, is we're going to take one of these methyl groups, so this is methyl group right here, and we're going to try to put it right next to these 2 different hydrogens, so something like this. So this is the hydrogen peak set B, and this is hydrogen peak set A. So you could take the yellow peak set right here and put it right beside the green. But if you had done this, then you would say, well, we would definitely get some kind of splitting pattern, but we're not seeing any kind of splitting pattern. So this is where splitting gets very, very helpful, is when we're putting our puzzle pieces together, we can say, well, does this assembly make sense in terms of the splitting pattern that we're observing? And this one definitely doesn't. So since we know that we can't put a yellow onto a green, what we could do is maybe take a yellow and put it on this kind of carbon that doesn't have any other stuff attached to it. So let's take this carbon, and I'll put one of my yellow CH3s right over here. So in this case, the way that I've drawn it, there are no hydrogens attached over here, and so this CH3 should maintain its singlet status. And as we go along, what I like to do is I like to start scratching out pieces as I use them. So I'm going to scratch out this piece right here, and I'm going to scratch out one of these 2 CH3s right here. So one other thing to think about is that since these CH3s were equivalent, since they're being displayed by the same peak, it means that we're going to have some kind of mirror plane equivalency to make these 2 guys show up under the same peak. And the easiest way to account for that is to put those 2 CH3 methyls on the same carbon. So I can take my other CH3 and I can just put him right here, and then that takes care of this molecule. And what you'll notice is as we start to remove puzzle pieces, the puzzle seems to begin to solve itself. So at this point, it seems like really we have 2 bromines left and we have a green guy left. You could really put this green guy on either one of these bonds, so I'll just put him, I don't know, on the bottom bond. But don't forget that this carbon right here is this carbon, and it needs one more squiggly just to maintain the fact that we have to continue building on that puzzle piece. Okay, so I'm going to go ahead and squiggle out that puzzle piece, which really leaves us only with 2 bromines. And if you look here, we only have 2 squiggles. So at this point, the puzzle's pretty much solved itself. We can put one bromine up above and the other bromine down below, and it really doesn't matter where we put the bromines in this particular case. And voila, it looks like we have a complete assemblage of the puzzle pieces. And so what we could do at this point is we could go back and double check our splitting and our integration and make sure that these 2 CH3s are equivalent. But I think hopefully at this point it's pretty obvious that these are equivalent and that this is going to show up, the way that it's going to show up as a singlet. But one other thing that you can do at this point is you can double check your chemical shifts if you didn't use that right off the bat. In this case, it's actually really helpful to look at the hydrogen set B and say that these hydrogens are geminal to the bromine, and so these should show up somewhere between 2.5 to 4.5. And if it shows up between 2.5 and 4.5, it looks like the peak actually is showing up in that range. So that just kind of tacks on a little bit more evidence to support our choice. So overall, this is actually the molecule. If we wanted to draw it out, maybe a little bit more pretty, we could put a bromine here, and then we could put, maybe another bromine right here, and we could put our two methyls right there, and then that's our molecule. So if this process was overwhelming, don't worry about it. This is a process that does take a lot of practice. So we're going to do more practice problems along the way, and after you do more and more and more of these, eventually I promise that this will become a little bit more second nature and a little bit more fun instead of just being intimidating, which it might be at this moment. So that's it for this practice problem, and I'll see you in the next lecture.